Good afternoon, everyone. It's now my privilege to introduce Trent Lloyd. Trent works in Canonical's sustaining engineering team, providing Ubuntu and OpenStack support, where Python is the primary language. Previously, having spent nearly a decade on the MySQL support team, he's no stranger to being thrust into other teams' production problems. Please give Trent a warm welcome.
All right, good afternoon, everyone. My hope today is to give you some insight into a few little different tools or different approaches to looking at some production problems that you might have seen. And hopefully there'll be something in here that's at least interesting to everyone. As was just mentioned, I've spent pretty much my whole career working in support, which means I get to enjoy other people's code bases and other people's problems without any real ability to prepare that environment for whatever debugging or whatever I need to do to solve that problem. This might sound familiar. Usually most people think of it as a legacy code base that they had no input in. But even on your currently non-legacy code bases, some of these approaches can actually still be interesting and useful in some cases. The first thing I'd like to do, I put up a quick poll on my Twitter just to get, I'm just curious what kind of approaches people use in their production environments. So at some point during the talk, if you'd like to pull up my Twitter and just answer that poll about what sort of tooling or what methods you tend to use when you're looking at production problems, I'd just be curious to look at that at the end and see whether that's kind of in line with what I was expecting, or maybe we've got a whole bunch of really awesome developers here, who knows. So Lafayette is my Twitter handle, and you can find that there. We'll look at that at the end. So right in the title of the talk, I've given you 3 things that we can look at. They're all kind of related. And I just want to kind of set the ground for what those things are. So when I talk about tracing, I'm talking about precisely logging every invocation of either a function or a line within a program precisely. So we want every invocation. We're not going to miss any. We know exactly what's happened in that program. By contrast, often when we're profiling, we're looking at sampling a program's currently executing line or function at a set interval. So instead of checking every single execution, we might simply ask Python 100 times a second, what are you doing now? What are you doing now? What are you doing now? The advantage to that is that over time, we can aggregate that data in some useful way and kind of get a good feel for what Python was doing most of the time without actually counting every single little item. And lastly, when I talk about debugging, we heard earlier today from Mina about interactively inspecting a program's execution state using a debugger. We can maybe set a breakpoint and inspect things. But I find that method of debugging is not often that great in production scenarios, particularly for online applications, because once we break in our debugger, at the very least, we're going to pause that request that's currently being handled. And most likely, we're actually going to pause all the requests coming into that application server while we're trying to debug it. And so using interactive debugger is a fantastic tool in the development phase, but if you're trying to diagnose a more production scenario problem, I find it's often better to look at other avenues. And so when I say debugging, I'm going to be looking more at diagnosing and fixing a bug. So when we're looking at profiling, well, what does a profiler do? Well, we're looking at exactly what code is being executed by the program over time on average. It's kind of similar to top or task manager. But instead of looking at your whole system and what processes is running, you're looking just inside of your Python process and what functions or what lines are being executed. Now, despite being 4 slides in, I've already lied to you all, because there are in fact 2 kinds of profilers. There are tracing profilers, which will actually exactly instrument every single execution and will know with exact certainty how often each line was run. But more commonly, we'll use a sampling profiler, which is the one that I talked about, where we just look at what we're doing maybe 100 times a second or even 1,000 times a second. And on average, you'll capture the majority of the code paths that your program is going through that aren't super, super fast. Now, when I say profiling, most people think about that in terms of improving performance. So maybe their application's not doing things as quickly as they want to, or most people's dreaded, my test suite takes 77 hours, and so I can only get 1 commit done per week. And so we look at a profiler to kind of help us with those kinds of problems. Which tests are slow, what parts of it are slow. But we can also actually use this in production scenarios that are not directly performance related, such as if a program is stuck. So if your application server is stuck, it's not doing anything, it's not outputting any log, we have no idea what it's doing, but we can see it sitting there, either using all the CPU or maybe doing nothing at all, we can use a profiler to look at it and find what actually is it doing. It's not outputting anything, but it's probably executing something. Or conversely, we might see that it's doing a bunch of stuff, but we want to kind of understand maybe it's running super, super slow. So it's not a typical performance problem where we want to make it maybe 50% better, but for some reason the whole thing's just running 1,000 times slower than normal. Well, by profiling it, we might be able to look at what kinds of requests are consuming resources, proportionally. What are the kinds of requests that are taking too long? We might find out exactly what is kind of getting us hung up. And so really what we're working with in Profilers are stack traces. So we want to know what functions are we executing in, and ideally we'd like to know the hierarchy of the functions that called into that. So the full call stack down into where we're currently executing. And we see these all the time in error reports. So if you throw an exception or some other error in Python, we'll get that nice stack trace printout. But in profiling, we want to really aggregate these from those hundreds of times a second into something that we can consume usefully, rather than looking at a single output. So how do we get a stack trace? Well, if we're in Python, that's super easy. We can just import the traceback module and call traceback print stack. And there's a couple other modules like inspect where we can problematically kind of step through that instead of looking at a string. And we have quite a few tools that can make use of this, which I like to call an in-process profiler. Python has one built in called cprofile. And there are a few others that kind of tweak this, PyInstrument and VMprof. But all of these profilers, they run inside of our Python interpreter, and they generally require some kind of setup in advance. So you might need to edit the source, import the profiling module, maybe make some calls to say when to start profiling, where to store the data. Or at the very least, such as in the case of cprofile, we at least need to edit the launch parameters of Python. So we need to pass -m cprofile. We need to edit that in whatever's launching our application, then we have to restart the program. And that requires pre-planning, which is not so great in these production scenarios I'm talking about, particularly if you haven't been able to set up in advance. And then if your error's a little less common, it might clear that error condition. So after you've restarted the program, you've started profiling, but now the situation you were trying to profile has gone away. Plus now our whole program's running with the profiler enabled, which has some overhead and produces a lot of data. And we might be able to add some kind of trigger mechanism to say turn that on and off, but again, that requires pre-planning, and it also may not work depending on how your program's gotten stuck. The actual mechanism you're using to turn the profiling on and off may not actually function. And again, because this is an in-process profiler, it's competing with your program within the Python interpreter for runtime. And so when it's doing the profiling work, it's actually taking away time from your program itself. So while these are all great in development, in production, this is kind of just like too hard. People tend to shy away from it because it's just not friendly to new users. It's not great in production scenarios. You have to do all this setup. So what other methods could we look at? Well, what if there was a way we could profile externally? And so instead of being inside of Python, we could reach in from outside from another process and look at what Python is doing. How might we do that? Well, we know that Python's already stored all this information in memory somewhere. It has to have it in order to give us that error print anytime an exception happens, which, because Python's dynamic, could happen at any time. So what if we could reach in from another process and read the memory of the Python interpreter? Well, we can do this, and in fact, this is how most C and C++ or other machine language debuggers work. So they use an API like ptrace, and the ptrace API, at least on Linux, allows you to control another process. So you can attach that process, you can tell it to stop, you can tell it to start, you can read memory, you can even write memory. You can actually change data or change executable code within the process with that API. And so we know as an external process, we have this superpower, we can reach in, we can read the memory of Python, we just have to figure out how to decode it. Unfortunately, Python doesn't just store that backtrace in the nice pretty string we're used to seeing somewhere in memory. And even if it did store that string somewhere in memory, we'd have to know where in memory to look, because you have like a 64-bit address space, and it could be anywhere. And so you need to figure those things out. So it turns out that's super easy. Just refer to this simple diagram. This is the layout of the structures in the C Python interpreter. And so the Python interpreter is a C program. It has C structures. And a C structure, given the same structure, the same text format of a structure in C, the layout of that structure and at what byte offset all of the things are stored is predictable. It doesn't matter what compiler you use, that's a standard. And so if we know the source code that our version of Python is compiled with, we know its structures, and we can figure out at what offsets we can find all this information about the Python interpreter state. We also have a global variable, here we go, called pythread state current, and this global variable points to the current Python thread. So in Python, we can have multiple threads. We may only have one, but this global variable points to that current thread, and then the thread keeps track of the top of its stack, the current calling function, and that calling function keeps track of the one that called it, and so on and so forth. So we just need to know how to find this pythread state. That might sound easy by name. It's not quite so easy. It's a little complicated. First of all, it's in a Python shared library, which gets loaded somewhere in memory. And because security is a thing, we have this thing called address space layout randomization, which means the library gets loaded somewhere in memory at random. And so we need to find out where that is, because scanning 32 gig of RAM or 48 bits of address space would take quite a while. So at least on Linux, there's a file in /proc called maps. And because we're root, and we need to be root to be able to do this kind of access, we can read that maps file to find out where the library is loaded. And then if we look at the Python binaries itself, we have debug symbols that will tell us, now that we know where in memory Python is, we now know the offset into memory that global variable exists at. And then from there, we can just follow all of these C structures, and it's really just a bunch of pointers to each other to find the actual code that's running. So the thread state has a pointer to the frame object, which is the current executing function. It's called a frame. And the frame object then will link to all of the other frame objects, like in the stack. And then from that frame object, it has then a link to an object called the PyCode object, and that actually has the file name and the line number that we're executing at. And so if 100 times a second we reach into Python, we follow all these pointers, we can get the file name, the function we're executing in. And so you don't really need to know about all this, but I just kind of find these little details like kind of interesting sometimes. How do these things work? So the good news is someone's done the work for us, and you don't need to do this manually. And there's a great tool called PiSpy. And so PiSpy lets you just launch the process, and you can, like I did in this example, which is straight from there at GitHub, just tell it to launch a new Python process. But much more powerfully, we can just pass it a process ID of an existing Python process, and we don't need to do any pre-setup on that Python process whatsoever. Out of the box, on Ubuntu, you started Python before you even installed PiSpy. You install PiSpy, you attach it, and then now we get profiling information from that Python process just by magic. What we see in this output is basically a live updating view. This is like a really cool mode. It's just like top, of which functions are executing and how much time they're using. By default, it samples 100 times a second, but you can configure that. And already this is kind of like a good way to understand what's happening on its own. So if your process is just a bit stuck, it's not really doing something, you want to know what it's doing, you might be able to get that just from this output. But it does have a couple of other interesting modes. One of them is a simple dump mode. So that's just a simple command line that prints out the currently executing call stack. That might be interesting in some limited cases. But what's even more powerful is we can visualize that data with flame graphs. And so flame graphs, if you've never seen one before, represent the data in your program. Along the x-axis is how much time. So we sampled the process 100 times in 1 second. And for each of those, we now divide the whole width of the page up into 100. And for each time we saw a process, we give it a little bit of that space. And so in this particular example, my I just want to highlight this particular example. We can see along the top, we've got a big red bar. That's the whole program. Obviously, the whole program was executing 100% of the time. Under that, we've got an orange bar that was taking up a lot of the time. But under that, you can see a yellow bar and an orange bar are kind of split, maybe 30-60. And so we know that that particular function, or in fact, those two lines, we're using about 30% and 60% of the time. And then within each of those functions, further down as we go down, we see what percentage of that function's time was in another function, and so on down the call stack. And what's even cooler about this is not just a static image, this is actually an interactive SVG. And we can actually click and zoom in on various parts of that image to find the bit that we're interested in. And so if I just bring it up in a web browser here, if, for example, I wanted to look at this particular function, I can click on it, it zooms right in. And so now those splits are a bit smaller, I couldn't see before, we can see a little better. And if I wanted to see what's happening here, I can click that and it expands it out. And so this is a really powerful tool to actually find out what my program is doing in much more detail and in quite a consumable way. And the other nice thing about PiSpy is this flame graph. Has anyone here used flame graphs before in any language? And you know that when you use them, it's like a four-step process, right? You run one command, you process it with another command, and then you finally get your SVG output. Well, in PiSpy, it just directly outputs the SVG file for you. So there's no intermediate data sort of wrangling that you need to do. And so PiSpy actually has a little bit of a history. It's not the first tool like this. And at least one of the more modern versions of this that first came out was called PiFlame. It was written by Evan at Uber, released in about September 2016. And it did the same sort of thing. It reached into the process and read its memory, but it wasn't quite as nice. So it used ptrace. It was written in C++. It didn't have that interactive view. It just outputted a flame graph. But it didn't give you the graph straight away. It gave you this text file, which you then had to process extra. And so if you integrated this into your own automation, it was great, but it wasn't super user-friendly. You couldn't just sit down with no prior experience, just run it, and then bang, immediately get good output. And so in April 2018, Julia Evans, she was so passionate about this project, she wanted to do something similar for Ruby called RBSpy. She took a 3-month sabbatical to write this tool. And she did a few interesting things that were different to how PiFlame worked, even though it was for Ruby. One, it was written in Rust, which is kind of hilarious because we're using Rust, which is a very memory-safe language. It goes to a lot of effort to make sure we're not reading memory out of order without locks. We basically throw all of that away and we're just reading memory straight out of another process while it might be changing it. Great use of Rust. But a great feature of Rust that works really well for this is a tool called bindgen. And so remember all those C structures I showed you? In PiFlame, they'd done a bit of work to kind of, for this version of Python, this is the structure and the offset. In RBSpy, we used Rust bindgen to automatically process the C headers for every different version of Ruby and just wrote those all into the binary. And so at runtime, it figured out what version of Ruby was running and then used the appropriate version of the headers without any manual sort of data wrangling. So that was all automatic. And then she added that interactive top-like view, which was really great because you can just jump right in and get some data straight away without any kind of wrangling or even have to copy the file to a web browser. And she embedded that automatic flame graph generation. So instead of this multi-step manual process, she literally copied and pasted the Perl program into the Rust binary, and it outputs and runs it automatically for you. Sounds a little kludgy, but it works well. It makes it super easy to use. And she's actually got a really good presentation about her process of developing this tool, and it's a great presentation. I'd highly recommend you search for it and watch it if you're kind of interested in the nitty-gritty, a longer version of that, those C structures I was showing you. And so there from RBSpy, that was April 2018, so only a year ago. This is relatively new tooling. Ben Fredrickson wrote PiSpy, which is heavily derived from RBSpy. It's also Rust. It shares a bunch of code with RBSpy, but just implemented all the special bits for Python, so it knows specifically for Python how to understand all that information. So far I've talked about profiling. Those are some of my favorite tools, some of the things I'm most excited about at the moment, because for me, I can apply such a tool to a customer's production system with no pre-setup. That's really powerful for me. particularly because a lot of the problems I work on in OpenStack, which is a very large Python code base, it was 1 million lines in 2017, who knows what it is now, it always likes to get itself hung up, and so it helps me quite a bit. But really what I'm talking about here is debugging production problems, and so sometimes we can pre-prepare for those production problems. And as I said, using an interactive debugger is not super helpful, and everyone's guilty of print debugging. I'm sure we've all written 1 million print statements into our production programs to debug. But there are a couple of tools that can make them a little bit nicer. And so one of those is PySnooper. And what PySnooper does is it allows us to trace a function's execution, not including just the function name, but actually also the values of all the variables and the exact code path that was followed. And it lets us do that just by using a function decorator or using a with block. And so instead of having to sort of guess where to put my print statements and all that sort of thing, we can just decorate a function like this with pysnooper.snoop, and then we get an output that looks a bit like this. And so what we can see on this is the exact code that's executing gets printed as it executes. And so if a loop runs more than once, it outputs the whole loop each time it runs. And each time a variable is set or the value changes, it also outputs that. And so now by using this, instead of manually putting prints in and then realizing you missed something and iteratively doing that process, I can just go, well, I know my problem's in this process. I can just call the snoop, I'll get a full trace output, and I can analyze that later. It's kind of like a past tense debugging instead of an interactive debugging. And so this is really good, again, for production where I can do some pre-setup, but there's low overhead. I don't have to trace the whole process. I can trace subbits, and you can even put conditionals on that. So if you know it was a certain user or something, you could add a conditional to only start PySnooper if a certain condition was met. And so this, I would suggest, is a much nicer way of doing print-style debugging, particularly for a production scenario. So the last kind of tool I want to talk about, now this is probably something you're not going to use straight away. It's a bit of an emerging technology, but I wanted to talk a bit about it because it has some interesting properties. And with Python right now, this only works at least on Ubuntu in the latest development release. It's not in the production versions. So again, it's a little bit of a preview. But we have this concept of tracing in the kernel called eBPF, which lets us do a bunch of tracing work inside of the kernel. And so instead of needing to actually process stuff in user space, we can have the kernel sort of trap the user program and then do a bunch of work inside the kernel in kernel space a lot faster than we might if we had to get all that information back out to whatever external process was trying to do that tracing. And so we have a concept called USDT, or user space defined trace probes, and Python defines a few of these probes, and they're on screen now. So we can actually attach to when Python starts and stops garbage collection. We can attach to when it tries to load a library, and we can attach to when it calls functions. That's what the function entry and function return trace points are. And we can also attach to every single time it executes a line. And so the ones that might be interesting here are function entry and function returns. So with this user space tracing technology, I can trace every time a Python function is executed. The nifty way, part of the way user space probes work, it's kind of crazy, but at compile time, Python inserts, or the compiler inserts, a single NOP instruction, a don't execute anything instruction on x86, and it's just there to kind of free up some space. At runtime, if I ask the kernel to trace this Python process, it will actually go in and replace in memory that null instruction with an interrupt to trap into the kernel. And so when we're not tracing the process, the code does absolutely nothing and it has no performance impact, and only when we want to trace it does it actually start trapping into the kernel. The overhead is so low that you may not realize that pretty much all of your Linux systems have these trace points on every time C does a memory allocation, every time a kernel function is executed, and you can even probe every time any function in any program is executed using the same technology. So these trace points are already everywhere. That's how we can know that when they're not activated, the overhead is basically zero. And so I can write a little script like this, and this is a tool called BPF trace. This is quite new. But I can tell it that I want to attach to a USDT, a user space defined trace point, for Python 3.8, and I want to trace every time a function is executed. And then I'm just doing a simple printf in this case, is a very simple example, to print the process ID and the function, the line number, and the file name. And so you can see the output of an example here. So I ran this probe, and I didn't have to modify Python except that it needs to be this new enough version with this function enabled. So as again, right now, that's only in Ubuntu 19.10 development. But then I get this trace output. Now, in this simple example, we're just outputting text. That is still a little heavyweight, but the power of eBPF and what eBPF itself is it's actually an interpreter inside the kernel. And so we can program the kernel every time this trace point is hit to actually do something for us. And so in this simple example here, what we do is we tell the kernel, trace function entry, but I only want to trace the function if it's called test1. And so if it's not called test1, it won't output anything. So you can see in this output, we only have the, well, I've called it func1, that's a typo, but nevertheless, they're the only ones that output, no other function output. And even more powerfully, I can get the kernel to do a bunch of statistics for me. So in this example, instead of printing, what I do is I ask the kernel to count how many times each function is executed. And so in kernel, in very fast machine code, it keeps track of each function, how many times it's executed, and it never actually sends that information back to user space until like maybe every 30 seconds or something like that. And so it's a very low overhead. And this is actually an example of a tracing profiler. So unlike our PiSpy example, this trace point will catch every single invocation of that function if you're maybe trying to look at something that's happening very infrequently. And again, we can do it with no preparation, so we didn't need to pre-prepare our system other than to maybe wait a couple years until it's on all our production machines. And this final example, it's a different tool. The BPF trace tool I just showed has its own little language, which means you can write little scripts on the fly. But there are also some pre-written tools that use the same technology but in a different way. But this particular tool is a bit nicer, and so when it shows the call stack, it actually indents it. So it shows you, this function's running under that function and so on. This is in a set of tools called BPFCC tools. That's the name there. These slides will be online, so you can check them. And so that's basically it for BPF. So it's just a quick little preview. You're probably not going to use that one yet. But as a bit of revision, profilers really can help with what is my program doing now. And we know about PiSpy, which we can use to do that with no pre-setup and no overhead. We also learned a little bit about PySnooper, which allows us to annotate specific functions and exactly what it's doing, exactly what code's been running, and what the values are of the variables, which is something we don't see in most of the profiling tools. They don't show us the values or the arguments to functions. We can do that with tracing. And this BPF and BPF trace is a really cool upcoming technology that applies not just to Python, but to actually all languages, Perl, PHP, Node, C, C++. They've all got similar hooks. In fact, most of them have better hooks than Python at the moment, sadly. That will let us do very fast analysis in kernel. The kernel can do the statistics and counting and histograms and all sorts of cool stuff. So I'm just going to have a quick look at our poll result because I'm just curious what people have said. About what sort of tools you might use in production problems. 22 votes. So that's kind of interesting. Even out of 22 votes, not bad. Everyone's guilty of print debugging. If it was multiple choice, I'm sure that would be at the end. But I mean, print debugging is actually really powerful and helpful. But in production where it's maybe harder to change the code, sometimes that tracing method, it might just save us some time. I'm also curious that no one's really using any of these commercial, and maybe I didn't make this clear, but there are a bunch of like commercial products like Honeycomb and others that kind of dynamically like instrument and profile and collect that in a nice dashboard for them. Is anyone here using any tools like that? Wow, that's fascinating. I kind of expect those may be more used. Really interesting. Well, I hope everyone learned something, and I think we have a couple of minutes for any questions if anyone has any.
Please say Trent.
Well, maybe 1 minute. 1 minute or one question.
And we have time for one quick question.
Regarding eBPF specifically, how complicated is it to write something complex? For example, getting a backtrace of an async program?
I actually haven't looked into async. So the question basically about getting backtrace something complex like async. There are some gotchas with the G-event style stuff. Some profilers work with it, some don't. Most of the ones I talked about do, but I've not looked specifically at async. So I would have to have a look at that, and maybe could let you know if you want to like Twitter me or something. I could try and look at that and see whether that works in any of those technologies. All right. Well, thank you all for coming. I appreciate it. I hope you found something interesting. And the slides will be online on my website or on my Twitter in case you want to look anything up later. Thank you.
And on behalf of PyCon.